Hi everybody, this is David Paul, and we have a webinar today on membrane degas, and it's being presented by 3M Liquicell. Amit Sengupta will be the presenter for 3M. This is a two-part series. The one 2 weeks ago was on forced draft, and then today is on membrane. It's a 45-minute presentation. I'll give a 10-minute intro, and then Amit will give the details for 35 minutes. Then we'll have 15 minutes of Q&A. As we go, just type your questions into the question or chat box, and then we'll get to it at the end. You'll receive an email immediately after this webinar with 3 survey questions just to see how well we did. So if you would just take the 10 to 30 seconds to fill that out, we'd appreciate it. The presentation is recorded. It'll be available next week. And you'll be sent a thank you email in the next day or two, and it'll have a PDF of this presentation, so you don't have to try to take a huge amount of notes. Just so you know, DHP and 3M do not have any financial relationships. There's no money changing hands here. We're just presenting this to give the industry information that we feel is valuable. I'm David Paul. I've been in water treatment since 1977, training consulting hundreds of plants since started this company in 1988. Have a Master's of Science degree in microbiology and reverse osmosis specialist 4 certified through DHP. Amit Sengupta is a 3M Global Senior Technical Specialist. He's worked in the Liquicell, that's the membrane degas business, for 26 years, and he is subject matter expert, holds a PhD in chemical engineering. So I'm just going to give a real quick overview and introduction, and this is a 50,000 foot version, and then Amit will give the details. So we talk about pre-RO and post-RO. Degasification is not so common pre-RO. The only one that I'm really familiar with is the HERO system, and we'll look at that here in just a couple of minutes. Post-RO is very common. So when, especially you want to remove CO2 loading from an electrodeionization unit or a mixed bed ion exchange system, then degas is very common. And like for drinking water, where you could have a well water that has hydrogen sulfide rotten egg gas, then commonly you run the water through the RO unit, the H2S gas goes through the membrane, and then you degas it afterwards to get rid of that nasty smell. So I'll go through an overview and then just briefly cover the 3 types, and then we'll get right to Amit's presentation. So water that's dissolved, gases that are dissolved in water, the amount of that gas that's dissolved in water is proportional to the amount of that gas in the atmosphere in contact with the water. It's all about diffusion, random motion from areas of higher concentration to areas of lower concentration. So if we have our atmosphere that has lots of nitrogen, some oxygen, and very, very little carbon dioxide, if we had water that had no gases, then by diffusion, we come back a little bit later and the gases would have diffused into the water. Well, we're going to reverse that for degas. So if we want to remove one or more gases from water, we just lower the concentration of the gas we want to get rid of in the atmosphere in contact with the water. So if we had a water that had lots of dissolved gases in it and we had no atmosphere, then those gases are going to diffuse out of the liquid. And if we were to continue to remove the atmosphere, then we would get essentially no gas in the liquid. And obviously it's going to be much more efficient if the water is in a very thin film, because the dissolved gases won't have so far to go to leave the water. So for forced draft and for vacuum, we're going to have packing, and we're going to spray water over packing so that the water cascades down in very, very thin sheets or film, so that the dissolved gases don't have far to go. So forced draft, basically we're just talking about taking our atmosphere, our air that we breathe, that's 78% nitrogen, 21% oxygen, and 0.04% CO2. We're going to blow that in contact with the surface of liquid. So if there are high concentrations of CO2, for instance, then we can remove CO2. That's called a decarbonator. So just like we saw before, the feed water comes in, sprays down over packing into very thin films. A blower blows air up, so now you've got the contact between the atmosphere and the water, and the dissolved gases that are in much higher concentration that are in the atmosphere will come out. And that again is forced draft. For vacuum, same type of setup, except for now we're going to remove the atmosphere. We're sucking out the atmosphere. So now we can get to even much lower concentrations of dissolved gases in the water. And then finally, membrane degas. Now, for most people, you're used to hearing the term RO membrane or NF membrane. This is not a water loving membrane. This is a hydrophobic membrane. Water doesn't go through this kind of membrane, but the gases can pass through. So still we want the water to be in very thin film. So membrane degas is going to have little tubes, and the tubes are going to be very close together so that the water is going to be on the outside and the atmosphere is going to be the inside of these tubes. If we were to put pure nitrogen on the inside of these tubes, then all the gases other than nitrogen would pull out of the water. Nitrogen, of course, would go into the water, but nitrogen's pretty inert, and not very many people care about how much nitrogen's in the water. If we were to pull a vacuum on those tubes, then essentially all gases would come out of the water. And for membrane degas, you can do both. You can have like a nitrogen sweep and vacuum at the same time. So before our RO, I mentioned that the HERO system is one system that actually does have degas in front of RO unit. And in this case, the purpose of the HERO system is to go to very high recovery. And very high recovery means that you have to handle calcium carbonate scaling. So a weak acid cation, that WAC, weak acid cation resin removes the hardness. To get rid of the alkalinity, the carbonate portion, you lower the pH to make as much of your carbonates and bicarbonates turn into CO2, and then you have a decarbonator. You got a degasification unit. And then now you can go to very high pHs, which gives you very high rejections, and you don't have to worry about calcium carbonate scaling. Other than that, it's not so common to have degas in front of an RO unit, but post-RO unit, very common. So in power generation, where you need high purity water for the boilers, you'll have some sort of degasification unit in front of the mixed bed ion exchange, and commonly is forced draft in power generation. For microelectronics, to get to less than 1 part per billion of TOC, total organic carbon, ozone enhanced 185 nanometer UV is required. Well, the UV whacks the ozone and turns it into oxygen, O2, and that would cause problems downstream. So then you use membrane degas downstream of the ozone enhanced 185 nanometer UV to get rid of the oxygen. So that's it for my introduction. Now we're going to switch to Amit, and he's going to give the details of 3M Liquicell's membrane degas.
Hello, my name is Amit Sengupta. I thank all of you who are joining here today. It was a great introduction by David. Thank you very much, David. Membrane degasification is normally abbreviated as MDG. Liquicell is the 3M owned brand name for MDG products, and it has been around for more than 25 years, and I have been with it since pretty much the beginning. My hope here today is to expand on MDG technology, products, and applications for you. There's limited time, so I want to get right to the subject without delay. The first thing I want to do, though, is to give you a top-level view. David already mentioned some of this. This is a view of the many different contaminants that must be removed. This is a top view, as I said. All the different contaminants that have to be removed are particles, inorganic ions, organic compounds, dissolved gases, bacteria, etc. Our focus here today would be dissolved gases. As you know, deionized water is used extensively in many industries. Some of them are listed here. Ultimate use of the purified water would often dictate the steps needed to purify. Although degasification name implies removal of all gas species, which could be CO2, O2, N2, volatile organics, hydrogen sulfide, ammonia, methane, gas bubbles, all this. But for this presentation, we'll keep our emphasis on decarbonation, removing CO2. Two of the most used conventional technologies for removing CO2 are forced draft tower that David mentioned and RO with chemical injection. Some of the key features for each are shown, listed here. The forced draft tower may allow contamination of water from air exposure. It will require booster pump to repressurize the water after the tower. It has very large footprint. On the other hand, reverse osmosis, you are basically using a caustic injection to convert the CO2 to ionic species, and at pH 8.6, all the CO2 converted to ionic species and rejected by RO. But it requires chemical handling, and there are process control issues and scaling of membrane involved in this. I will, of course, explain the liquid cell in more details, but the first question why customers is why customers would be interested in the membrane degasification at all. What are the drivers? And here in this page, we are providing some answers. There are some unique benefits why customers are adopting MDG increasingly. Consider number one, no chemical is needed. Number two, great gas removal performance in properly designed systems. Number three, extremely compact skid mounted systems. Number four, their systems are modular and mobile in nature. Number five, inline operation under pressure, so no need for booster pump. And number six, ease of startup and shutdown, etc. Many of these are very compelling reasons for liquid cell customers. One quick disclosure here, just to emphasize what David already said. MDG is not a water filter, and it is not a gas separation membrane, such as used for CO2 removal from natural gas, for example. The role of membrane in MDG is to keep two phases separate without dispersion, as I show in the following page. The membrane in MDG is almost always hollow fibers. Very small diameter. You can see it's about 200 to 220 inner diameter, and very thin wall, 40 to 50 micron, made of polypropylene membrane, which is naturally hydrophobic. The membrane is actually non-selective and microporous. with a nominal pore size in liquid cell membranes being about 30 nanometers, 0.03 micron. There are two membranes that we have, X40 and X50, of which X50 is the ideal one for CO2 removal, even though it can also do oxygen. Now, here's the key principle of operation for an MDG. Follow the picture. Water is flowing around the hollow fiber. A single hollow fiber is shown in the picture. Water is flowing around the fiber, but it cannot intrude or flow through the pores that are shown in the picture. Water ingress is prevented by surface tension effects, even when water is under fairly high pressure, which can be as high as 200 psi. The pores in the membrane wall stay gas-filled and it's free of water. Now, if you apply a vacuum or a sweep gas inside the fiber, you create a driving force for gas transfer. The gas molecules will diffuse from bulk water into the water-gas interface, as shown in the photo. And then the gas molecules will immediately be stripped off into the gas phase. It is as if you have frozen the sort of gas liquid meniscus in space, if you will, while allowing gas and liquid to flow independently. This is the key feature that leads to the benefits I talked about in the earlier slide. Okay. Now, the hollow fiber membrane is the key, of course, but it is usable only after it is converted into modular devices that we call contactor. There are different contactor sizes for a wide range of flow rates. You can see on this map, we identify products mainly by physical dimensions. So a 10 by 28 means diameter of about 10 inch and length of about 28 inch. Apology to the metric enthusiasts. The largest contactor, that is 14 by 40, can handle more than 400 GPM of water flow rate. Apart from the contactor size and corresponding flow range, other options that are available would include the housing material, seal material, connection port type, connection sizes, etc. Of course, I'm not going to go through this page in detail, but the point here is to give you basically a glance of the many available options. On this page, I am showing a general deionization process scheme, and I'm trying to point out where MDGs can be located. After pre-treatment, the water can be deionized by either taking it through the RO route or through ion exchange resin bed route. In case of RO, MDG can be located in between the first and second pass, or it can be after RO. In case of resin bed, MDG can be located after cation bed, and it can substitute for the forced draft degasifier very ably. And as you see, the EDI, which is used a lot these days, frequently before EDI, degasification is used to actually help EDI process be more efficient. I'm also on the right side of this page. I'm showing what we call downstream degassing steps, where the DI water made from the processes just discussed can be further purified for specific purpose in different industries. Like I show here, water for steam generation, water for injection in pharma industry, ultra pure water for wafer processing. All of these, there are specific applications for MDG, although we are not going to cover that today. And one fundamental point across effect of water pH and relationship with alkalinity and CO2. As you know, there are ionized form of inorganic carbon. The equation on the screen, it's the basic equation, how CO2 as a gas dissolves and ionizes into bicarbonate and carbonate ions. As the pH is increased and decreased, the relative ratio of the bicarbonate to free CO2, as we call the physically dissolved CO2, would change. And the chart is showing how critical pH is. At if you see at less than 4.5 pH, almost all the CO2 in water is free, whereas at pH of greater than 8.6, all of it is in ionic form. And so since only free CO2 can be removed by MDG, it is essential that we pay attention to the pH in the effluent or influent rather to the liquid cell. At this point, let me talk about operating modes. The same MDG can actually be operated in different ways. One can use a sweep gas, one can use a vacuum, one can use a combination of sweep and vacuum that we call the combo mode. And in the sweep gas is used, and the choice of sweep gas depends on the species that you're trying to remove. If you're trying to remove CO2, you can actually use air or even nitrogen sweep to get rid of CO2. On the other hand, if you want to remove O2, oxygen, you can use CO2 gas or nitrogen gas as sweep. And vacuum mode is used to remove all dissolved gases, gas bubbles. And therefore it is preferred when people want to remove everything that's dissolved in gas. And combo mode has the best degas performance because it allows the partial pressure of the oxygen gas to be suppressed very in a major way, so that the transfer rate is high, gas transfer. One special option is to use a blower in suction mode, that's shown on the right side, the lightmost box. This is a less expensive option than compressed sweep gas. As we said, modular nature of the contactors, it allows connecting in parallel or in series to make what we would call a degas skid. The illustration here is a generic PNID in combo mode, nitrogen and vacuum. If you follow the arrows for water, the feed water is split in half, and then each half is taken through two contactors in series. And so what we have here is what we call a 2x2 system, 2 parallel and 2 series, a total of 4 contactors. Sweep and vacuum are normally manifolded directly to individual contactors. This is basically for convenience and also to improve the gas transfer rate. Depending on the required system flow capacity, You can increase or decrease number of contactors in series or in parallel. You can add redundancy to the system. You can add new capacity to your existing system. You can turn down your flow if you want, operating at reduced flow. You can adjust sweep gas flow rate, purity. You can adjust vacuum level. You can have many levers to adjust. And this is what gives MDG technology the unparalleled flexibility. This is a case study here. This is an RODI system. The MDG is placed after a 2-pass RO, operated in vacuum only, as you will see under the system specs. It is, if you look at the specs, it's designed for 400 to 700 GPM flow rate. Feed pressure is 105 PSI, water pressure. It's a vacuum only mode, about 27-inch of mercury vacuum. This gives about 75% removal of CO2. A photo is shown in the box, the photo of the system. And one note worth mentioning is the water pressure. As you see, the water coming in is at 105 PSI, and typical pressure drop through an MDG system, degas system, is anywhere between 5 and 20 PSI. So the water coming out of the MDG is at quite a high pressure. And that's a major benefit because the pressure is high enough to supply subsequent steps after the degassing without any need for repressure pump. A second case study I'm showing here, the MDG before and after installing MDG in a deionized water system. This is not RO, but I'm showing you as an example. The water processed between cycles was 2 million gallons before, and after MDG was used, they were getting 7 million gallons. And look at the number of regenerations that they could reduce in a year from 36 to 10. And if you are looking at certain cost per regeneration cycle, regeneration of the bed, resin bed, you can see that overall it will add up to very significant cost savings. This is real money. In this particular calculation, customers saved more than $175,000 a year. And it's a bunch of savings here: lower cost of regeneration, lower cost of resin replacement, or excuse me, resin shipment to or from site, lower downtime and labor, and of course, no chemical to regenerate. Quickly, a couple of system photos. The first one is a degas system that used 14 by 28 membrane contactor. The next one is a 10 by 28 contactor before EDI. There are many systems that have been installed over the years, millions and millions of gallons of water being processed, but these are just some examples. Now, at this point, some recap. Some questions to evaluate suitability of MDG in your plant would be as follows. Number one, does water contain particles? If it does, you may need to pre-filter. We recommend 5 micron absolute rated filter. Next, is the water, does it have stuff in it that reduces its surface tension? That's an important question because lower surface tension make the MDG less effective. Next, are there species in water that may decrease membrane lifetime? For example, ozone or hydrogen peroxide or UV, etc. Exposure to these oxidants should be restricted to have reasonable membrane life. Do you need chemical CIP? Clean in place. Do you need to sanitize the MDG after cleaning? All these questions are important when you're first considering MDG for your system. Answers to these issues greatly help in decision making. The last topic I want to discuss is to help customer with system design. We use a macro-enabled Excel sizing sheet that we call GasCAD. GasCAD is a little program that is used extensively by us and our customers or selected customers. If you look at this screen on the lower left-hand side, you enter your process parameters like your flow rate, your temperature, number of contactors, your vacuum level, sweep gas flow rate. This, by the way, is being used in air combo mode in this system. And as you enter the info, you will see on the top right box with blue box the results from the GasCAD calculation. And you can save this whole set of conditions as an option, like you see on the top right, copy option. You can have up to 6 options that you can run and save for comparison purpose. And after you run the GasCAD, you end up with what we call a system sizing summary, an example shown here. Again, it basically lists for you the contactors that you have chosen, water flow rates, gas spec, effluent CO2 spec, etc. You can see on the first option that under high water flow rate and ultra low CO2 spec, you can see that you are able to get to between 0.2 and 0.5 ppm of CO2 starting from 25 ppm coming in. And you can, this is for a 300 GPM flow rate and 25 degrees C. In any case, these different options are what you need to get. This is generally the first step in designing your final system. After you choose the optimum operating scenario, then you may start more detailed system and equipment design. At that point, you will probably start working with your favorite skid builder or OEM. Now, there are many sales tools and other technical resources that have been developed for Liquicell product line, as I show here. We have data sheets. Each product has a data sheet developed for it. It lists all the detailed information as well as some nominal performance charts on the second page of each data sheet. You have housing drawings available. You have generic PNIDs available. You have startup and operating guides. You have cleaning guide. And of course, you have GasCAD. which is accessed by request only, and it requires online training. Your local sales rep, sales manager, or distributor is likely your first contact, but there are central technical specialists such as myself. We are happy to help. We want you to understand and learn about the technology. What is LiquidCell and why LiquidCell? We want to discuss your application. We answer your questions, help size your system, troubleshoot your system. We'll be happy to help. And here I come to the end of the talk today. The material I covered would probably take me, if I go through the details, about 8 hours. So it's kind of difficult to condense all that into 30-minute talk. I did skip a few pages for the sake of time, but of course they would be included in the material that will be sent to you afterwards. I tried as best as I could to give you some ideas about the technology and hopefully start some thoughts in your mind. I would thank all 3M and LiquidCell team members who helped me with this presentation, Scott Willis and Emily being two that I want to mention by name. Please let us know if you have questions or want any clarification. I thank you again for your time, and I will be happy to take questions. Thank you.
Hi, this is David again, and I'm just going to be here for just a few seconds just to introduce the question and answers. And just to remind you that if you have a question and you haven't written it already, please do so now. So Amit is going to receive your list of questions. He's going to take them one at a time. He's going to read the question and then give his answer. And as we'll see later, any questions that aren't answered now, he will respond by email. So Amit, if you would go to questions now.
Yes, I have the chat box open on my screen. First question that I see is, what is the general purpose of doing degasification of water? The answer, of course, would be that it is used to remove all the gases that are not desirable in the water. And there are many steps, many processes where it is necessary to get rid of dissolved gases. And that is the purpose of degasification. Let's see. What is the LSI limits? That's next question. For contactors for feed or treated water, especially when free CO2 is removed and pH will go up. Ideally, we would like the LSI to be a negative number, minus less than 0, and because we want to make sure the membrane doesn't get scaled, for example. But even if it gets scaled, it's a slow decrease in performance, and it is easily cleaned, the membrane is, and therefore even if you have pH going up as water flows through the contactors, it is possible to restore the membrane if it's necessary. Next question, what is the CO2 concentration in water after a forced degasifier? I assume you're talking about forced gas tower. For the forced gas towers, typically we hear that CO2 concentration is around 10 ppm, parts per million, or milligrams per liter. Between 5 and 10 is typical. And many processes downstream would require much lower CO2 concentration. And as I have shown, the liquid cell, the MDG, can take it down to about 0.5 ppm, which is a tremendous difference between MDG and forced draft. What is the maximum water temperature the gas membranes can handle? The membrane is rated, maximum temperature rating for the membrane is about 85 degrees C, but that is only for occasional exposure, particularly when hot water sanitization is performed. In general, we recommend the operating temperature be less than 60 degrees C, preferably even less than 50 degrees C, depending on the housing material that is chosen. Next question is heat sanitization recommended for these membranes? It entirely depends on the kind of use that this water is intended for. In case of food and beverage industry, they always require hot water sanitization. That can be done with these contactors. Not all material of construction, but we have stainless steel contactors that can be hot water sanitized up to 85, and it is routinely done by beverage customers. What is the maximum operating pressure? The membrane can actually tolerate up to 300 psi pressure. However, the housing and the seals, all those things come into play when you're talking about high pressure rating. Most of our contactors are rated between 100 and 150 psi. The special high pressure contactors, they are made with RO housing and designed such that the water pressure can be up to 300 psi. Question: what is the benefit of using the contactor in series as opposed to parallel? The series, more number of contactors you put in series, more amount of gas you will remove as you put more, as the water goes through more and more number of contactors, you are removing on a percentage basis, higher and higher percent gas is removed for the system. On the other hand, if you are looking to increase the capacity of your system, increase the flow throughput, then you would put more number of contactors in parallel. By increasing the number of contactors in parallel, you are going to increase the total number of flow rate that the system can handle. Question: can GasCAD do O2 removal calcs? Absolutely. I mean, it is used for O2 as well as CO2. I wanted to focus on CO2 for this webinar, but absolutely it is used for O2. Has the process been used for ammonia removal? Well, ammonia removal is slightly more complex as opposed to regular decarbonation or deoxygenation. But yeah, we have sold liquid cell contactors, quite a few, significant revenue for ammonia removal application. In those special cases, just to point out, it is essential that we work with OEMs to establish the right process parameters and do pilot trials if necessary, so that we can design the right system. Question: are the systems hot water sanitizable with 185 water? Let's see, 85 degrees C. I think that is 185 degrees F. So yeah, the answer is yes, it can be done. And are all elastomer components compatible with USB class 6? No, that is not the case. You have to choose very specific seals. For example, there is high purity Viton that is something that can be used or are used by customers for very high purity applications. What is the difference between conventional deaerators and membrane degassers in deoxygenation application? Advantage of 3M here? Well, a couple of questions, sort of loaded questions here. There are many differences, similar to what I tried to describe in the middle of my presentation. There are some unique benefits of membrane degassers that's the reason increasingly more and more customers are opting for that. In deoxygenation application, this is going to be, the answer would be similar. For deoxygenation in particular, the membrane degassers are able to bring the dissolved oxygen level down to less than 1 parts per billion, which is something that we do not believe deaerators can accomplish. So it is one of the best stories to tell for liquid cell that it can do that. And the advantage of 3M is the owner of the liquid cell brand, which has been around for 25 years or more. And we have name recognition. We have developed many products, excellent products over the years, and continuing to develop new products. And that is what we would claim the advantage of 3M. Question: in case of biofouling, what are the options? Great question. As you know, it is not possible to not have biofouling in many situations. It is possible to chemically sanitize the membrane. It is done by using low concentration of hydrogen peroxide or chlorine. It is not, it's important to note that exposure to these oxidants should be restricted, but they can be sanitized to get rid of biofouling. And of course, they can be cleaned with hot sodium hydroxide or potassium hydroxide solutions. And so with that, along with chemical sanitization are done routinely for liquid cell. Next question is, it was mentioned that cleaning is possible. Is this CIP? Yes, you are correct. By CIP, we mean clean in place. So cleaning is definitely possible. Generally, we recommend uh, either caustic cleaning or acid cleaning or both. There are some situations where those types of cleaning would not do the job, and under those conditions, we normally get those contractors back on site here, and we do some special treatments and cleanings to help. But yeah, chemical CIP is done routinely by customers in the field as well as in on site here. Next question is the same question. Liquid cell membranes be cleaned if they lose efficiency, or do they have to be replaced? It's all a question of relative importance. As I just mentioned, they can be cleaned, and in most cases, performance can be restored to high enough level. There would be some situations for sure where the membrane is damaged beyond repair. And if that is the case, and if we do find out that is the case, then it is necessary for customer to replace them. If the pH of the incoming water is around 6 to 7, will there be any benefits in installing liquid cell to the customer in a DI system? I did mention in my talk about how critical pH is. If your water going into liquid cell is at pH of 7, only a small fraction of the total inorganic carbon is available as free CO2, which is the only component that we can remove. That any, not just liquid cell, but any membrane degasifier trying to remove CO2, they can only remove what is called free CO2 or physically dissolved CO2. So if your pH is between 6 and 7, depending on exact pH, only a percentage, anywhere between 40 to 60, 70% of CO2 can be removed, and that would be the benefit. But of course, it cannot remove 100% if your pH is 7. Next question, at what point will you realize that you need to introduce degasification membrane in your normal water treatment process? Well, it really is driven by your need for performance. If your existing system does not have any kind of gas removal process, and if your downstream processes require gas to be removed, then it's essential that you consider the degasification. It is not necessary for all water treatment processes, but increasingly for applications that require higher purity, you would be needing water without or reduced gas concentrations. Next question is how often the contactor's membranes require cleanings or sanitization. If site does not have hot water, can we do chemical cleaning? The frequency of cleaning is, of course, we don't have a single answer to that. It all depends on the quality of water going through the contactors. We have had in microelectronics industry, we have had contactors in the field running for 10 years or more without needing any kind of cleaning. But then that is ultra pure water. For beverage industry, for example, the frequency of cleaning may be once a week to once in 6 months to once a year. It all depends on the quality of water. And if site does not have hot water, can we do chemical cleaning? Absolutely. Chemical cleaning is done routinely on liquid seal contactors, and not only cleaning, but it can be sanitized as well. This will be the last question. What is the difference between IND membrane and the X40, X50? Obviously, you know a lot more about liquid shell than many others. IND membrane, actually, it is not just the membrane, it's the whole contactor that we call industrial contactor. But this is a membrane that can work similar to X40 or X50. However, it doesn't go through the same level of QC, and it doesn't have the same temperature and pressure ratings as the X40, X50 contactors. Hope that answered your question.
Thank you so much, Amit.
Sure.
Both for the information and for allowing so much time for so many questions. This is excellent.
Yeah, I realized that I could have spent more time and shown more slides, but I was afraid that I would, pass the limit.
No, you did perfectly. Okay, so we answered all the questions, but if you have any other questions, you can contact the address here. And again, you'll receive a PDF of this presentation here in the next day or two, and all of this information that you've seen will be there. And just for your information, we have a high purity water seminar that includes degas, and we have lots of training programs. So if there's both classroom and hands-on, so if there's anything that we can help you with, we'd appreciate it. We thank you so much for attending. You'll receive an email as soon as we close this webinar, and it just has 3 questions. It won't take more than 10 to 30 seconds. So if you'd do us the great favor of just answering and letting us know how satisfied you are with this webinar, we would really appreciate it. So thank you so much. We'll look forward to seeing you at our next webinar. Bye-bye.
Bye.